Good morning, everyone, or afternoon or evening, depending on where you're coming from around the globe. Welcome to this very first lecture in our latest series on microplastics. Just while we're waiting for a few people who maybe haven't joined us yet, I just want to maybe do a little bit of announcement of some upcoming events. And for those of you who are not overly familiar with the IIES, just tell you a little bit about some of the activities that go on within the Institute. So my name is Doug Evans, and I'm the director of the International Institute for Environmental Studies. And we are, as you will know if you have explored our website, a collection of, at this point, more than 20 universities and government agencies around the globe. And we do have some annual events that I just wanted to let everyone know about. We have an annual science and policy workshop, and this year we'll be holding that workshop in Santiago, Chile, and it will be on the 11th and 12th of December this year. And want to invite any of you who are interested to join us. You do not have to be at a member university to attend the meetings. We welcome anybody who is interested to join us there. And there is a page on our website that you can find out more information about the workshop. We will be having a session on microplastics as well as other emerging contaminants at that meeting. We'll also be having sessions on blue and circular economies and a particular focus on strategic and critical mineral extraction. So I do hope that some of you will be able to join us in Chile. It's always an excellent opportunity to get together and to meet people from other countries and to discuss how science is done in different jurisdictions. Following that meeting, we will also be holding our international graduate student forum, and that will be in a smaller city south of Santiago called Puerto Montt. And the graduate forum, we usually limit it to about 50 to 60 graduate students, just so we keep a small group. But we do want to encourage any of you who are interested, graduate students, to go to our website, and you can find the information about the upcoming graduate forum, and there's a registration page there as well. If you are a graduate student at a IIES member university, we do have some travel grants available to help offset some of the costs of traveling to Chile. So I hope that some of you will be able to join us. The other thing I just want to mention is that these lectures are recorded, and then they will be posted on our website. So if there's anything that you want to review after the fact, or if you happen to miss a week and you want to catch up, you can always go to our website where you'll be able to hear the talk again. So at this point, I'm going to turn the meeting over to Professor Chen Gu. Chen is a professor at Nanjing University and associate dean in the School of Environmental Science and Technology, Environmental Science and Engineering, I think. And Chen is going to be our host for the series. And so I'm going to turn it over to him to introduce our speaker for today.
All right, Doc. How are you?
Good, thank you.
Okay. So yeah, we will start for the IIES, the Environmental Online Seminar Series. This is for the microplastic in the environment. So our first speaker is from University of Trent University, Canada, Professor Julian Aherne. He's a faculty member. First of all, I just give a brief introduction of Professor Aherne. He's a faculty member in the School of Environment at Trent University, Canada. During the last 3 decades, his research has primarily focused on the impact of air pollution in semi-natural ecosystems and the determination of critical loads in support of UNECE Air Convention and the Canada U.S. Air Quality Agreement. During 2017, he began working on microplastics, initially focusing on the atmospheric transport of microplastic into remote lake catchments. But this expanded to an interest in the use of biomonitors of microplastic deposition, catchment budget to quantify microplastic residence time, microplastic in Arctic lakes, and also the microplastic signatures in urban stormwater ponds, and the fate of microplastics in wastewater treatment plants. So let's welcome Professor Aherne for his lecture. Hello,
Chen.
Julian.
Thanks very much, and Doug. Thanks very much, Doug. I look forward to the meeting in Chile.
Okay.
I guess I should share my slides. Hopefully this will work. And I guess you can confirm that that is in, everyone can see it, you can see it, so it's fine to start, I assume. Excellent.
Yes. Mm-hmm.
Thanks very much. Thanks very much for the introduction. And as you mentioned there, it's about 2017 that I became interested in microplastics. And I was happy that Doug asked me to do the introduction here. And the introduction is just a general introduction, I think, so that everyone's on the same page. It should be more or less, I think, basic knowledge or common sense for everyone here on the presentation today. So I think I'll just go over some background that people know about already. I should note that, of course, even though I'm interested in microplastics, I do microplastics research. Of course, I'm not the person who does the research. And of course, there's a bunch of students in the lab who've been doing the work, or currently doing it, and have done it. And I've noted them there. And especially thanks to Harriet, who I've stolen a bunch of slides for. And I think I'll note overall, I've recycled a number of slides from different sources. So you may recognize these slides from online or other presentations. And I also note there's just an icon there in the bottom left-hand corner for the priority project. It's an EU cost action project. And it just brings together people who are working on and collaborating on microplastics. It's a good forum to connect with others who are working on microplastics. And I think there's some interesting opportunities for student training as well through that, and it's online. It's easy to sign up. I think there's a couple of hundred members, so I would just note that that might be something that's of interest to people on the call. Today I won't talk about toxicity. I know that's going to be some presentations later in the seminar series that will cover toxicity. I might mention it once or twice, but I won't discuss it at all. And I'm not going to focus on analytical techniques, but I will introduce a kind of a general analytical workflow, really just something that represents the work or the workflow that we currently use. And I thought I'd start with my last slide. So essentially what I've noted through this talk are some challenges to microplastic research. I'll note them here as an introduction. So if you stay awake for the first 5 minutes, or if you stay focused for the first 5 minutes, you've got most of the takeaways. But also I'll revisit these at the end. And maybe some of these are just what I would say is gripes that I have, or yeah, some complaints I have. I think the first thing I would note is that the common units that are used for microplastics, the ones that are most widely published in the literature, are far too simple, and they lose or they miss a lot of detail. And as most people know, microplastics are widely reported as the number of particles in a certain media. The science is rapidly changing. As I mentioned, I started looking at microplastics in 2017. And I think over that time period, the methods, how the science is being carried out, has rapidly changed. And so that presents some challenges, as a method that you use 1 month may not be recommended the next month. And of course, it means that, yeah, there are continuing improvements in terms of how we can assess microplastics in the environment, but it also presents a challenge just in terms of looking back to previous research. This is I noted that Doug already, this is a little bit of a joke, that the science can be fishy. And by this, I mean that much of the microplastic research started in the marine environment. So many of those methods were associated with marine procedures, and as such, they don't easily transfer. Maybe that's microplastics research is very interdisciplinary. And so you have some transfer of methods that may not be the ideal methods. And again, given that it's rapidly changing, there's some reinventing the wheel in terms of standard methods that have been either forgotten about, or people from an interdisciplinary background moving in to carry out measurements in, say, terrestrial environments and ignoring perhaps several decades of research in those environments that have been monitoring other pollutants. Again, noting back to the units, we'll come to it. Everyone knows that microplastics are defined as plastic particles less than 5 millimeters, but that there's quite a large size range there, and that size range is important, but it's very much ignored by the common units we use. And given that the science is changing, given that there can be this, what I would say, is differences in terms of how we may measure microplastics in the environment, comparison is difficult at best. And I think this is a real limitation. And I'll come back to it again, in that in the last 10, 15 years, there's been an exponential growth in microplastic research, and an exponential growth in the publications of these studies. But given the variation in methods, it's difficult to have an accumulated knowledge in that many studies, the difference that we may see across sites or across regions aren't actual difference in the environment, but potentially difference in the methods in terms of collection, extraction, or counting of microplastics. Another thing that's well accepted now is microplastics are everywhere. Why that's a challenge is that, of course, because they're everywhere, that's easy in terms of contamination. So contamination can be an issue. And again, as we move to background regions, we want to make sure that what we're measuring in the environment is well above the levels of contamination that we may be introducing to our work. Another thing to note is that, of course, it's difficult to separate microplastics from the environment, and that means as we sample environmental medias, we have to extract the microplastics from those environmental medias. The ideal situation, of course, is that we extract them and that they're as clean, as pristine as possible so that we can identify their polymers. But it is a challenge, and that's perhaps one of the bottlenecks of the current workflows, or the current workflow for most people, is extracting those microplastics and having them as clean as possible, as pristine as possible, so that they can be analyzed. At least for our lab and the work we do, current methods are tedious and time consuming. And again, another bottleneck. It is a very manual process. And I know every equipment manufacturer has promised or is promising new methods and faster procedures to measure microplastics. But often many of those promises don't actually come through in practice. And so we still find that a lot of the work is tedious, or there are ways to speed up that work, but there are shortcuts to that, and there are some losses along the way. Lastly, I'll come back to this again. I'll come back to all these points again. We know that microplastics slowly degrade in the environment, and as they break down, they become microplastics. And given that it takes somewhere between 20 to 500 years for microplastics to break down, I ponder on whether we're at the tip of the iceberg in terms of the concentrations that we're currently seeing in the environment. And again, I'll come back to that. The other thing I'll note, I never mentioned, Doug suggested that I cover about 25, 30 minutes of an introduction, and then that I focus a little bit on some of my own research. If I have the time, I'll cover about 10 or 15 minutes on some work we've been doing with biomonitors. But again, I'll be mindful of the time. Before jumping into microplastics, of course, I have to cover a little bit in terms of plastics, and it's currently said that we're in the age of plastics, and it's clear that plastics have played a definitive role in delivering much of the socio-economic advantage of modern life, and their production has outpaced that of almost any other material since about the 1950s. And again, of course, everything we carry, everything we wear, it's plastic. And why plastics? Well, I'll just quickly run through this list. They deliver unparalleled design versatility, so high ductability or ductility. Plastics can be used at a wide range of temperatures. Plastics are chemical and light resistant. Plastics are very strong and tough. They have a high strength to weight ratio of stiffness and toughness. They're corrosion resistant. They have high thermal and electrical insulation properties. They're lightweight, outstanding durability, and they're inexpensive. And so, given the range of properties and the low cost, this has driven the annual worldwide demand. And again, if we look at this global production accumulation and forecasted future trends, we can see here the growth of plastics from 1950 with up to 2017, and then a projection in the future, into the future up to 2050. Under this UNEP study, that by 2017, global production was 438 million tons. You can see here. Again, as you can see, it's forecasted to 2050 to reach more than 1,000 million tons. Of that, or over that period, over the period of 1950 to 2017, there's 9,200 million tons, accumulated tons of plastic that was produced. Of that amount, less than 10%, 700 million tons has been recycled, and more than 50% has been discarded. 5,300 million tons have been discarded as waste. And just a note in terms of that production, given this exponential increase in terms of production since 2000, so between 2000 and 2017 in this study, more than half of all plastics ever produced have been produced in that 17-year period. So we see this rapid increase, and of course that increase is forecasted to continue, and again we'll see this doubling of the amount of plastics in shorter and shorter periods of time. In terms of what plastic is used for, of course it covers a wide range of things. I've mentioned, we know it's in our clothes, it's in our cars. It reduces our energy consumption because cars are lighter, reduces breakage because we've got more secure packaging. But one thing to note is that about 40% of what's produced is packaging, and this is packaging, essentially material that has a short lifetime, or it's at least manufactured to have a short lifetime. And this introduces what I would say is a bit of a design flaw in that we have a material that has high durability, but it's being used for a product that has a very short shelf life. Ultimately, with this disposal, we have leakages in the system and mismanages of waste. Again, more than 50% of all plastics ever produced have essentially been disposed of. And this mismanagement of waste has meant that, of course, plastics have entered into the environment. And so this durability and increasing use of plastic has caused, I would say, a major waste management problem. Many jurisdictions can't keep up with this waste management problem, and as a result, there's leakages into the environment. There's many images like this on the internet. We see large piles, at least here in the top right and image A, we see large piles of plastic waste in terrestrial environments. We see them in riverine environments. They make their way into the ocean and marine environments, and of course, back onto the beach. And once plastics are in the environment, over a certain period of time, they'll age and start to break down. And I won't say too much about this. I think, again, this will be a future guest lecture that will focus on aging of microplastics. But of course, there are biological, physical, and chemical actions that help to break these plastics down. In terms of biological, there can be algae or fungi, or even ingestion of particles by animals, and within their gut, they'll break down further and they'll pass them and cause biofragmentation. Physical, of course, is that abrasion. But also ultraviolet light is well recognized as perhaps one of those agents that rapidly ages plastic. And of course, if you're in the marine environment or in the terrestrial environment, you may have differences in terms of how long it takes to age. But in general, there's studies out there that say somewhere between 20 to 500 years, plastics break down into the environment from plastics into microplastics. In terms of microplastics, the occurrence of these small plastic particles on beaches and in coastal waters was first reported in about the 1970s. And it wasn't until about 2004 that the term microplastics was first coined. Much of the research and the initial research focused on marine environments and beach environments. And I would say this first few decades perhaps were dominated by marine research within the oceans, within beach systems. But microplastics research now is, of course, expanded to cover all ecosystems. And what we've seen, as well as exponential growth in microplastic production, there's been an exponential growth in the publications on microplastic research. And this is one of the many studies out there that has reviewed the number of articles that have been produced over time. We can see here from 2006 onwards, just shortly after the term microplastics was first used. And we see this exponential growth in publications on microplastic research. I'll note, and I say 2016, but I actually think there was a paper out in 2017 by the same authors that by 2015, 2016, the first study on atmospheric microplastics was published. And this was based in Paris, France, where they looked at deposition of microplastics in Paris and also a suburban area around Paris. This review did note that there were hotspots of microplastic research in the marine environment. So many of the publications focused on the marine environment, on freshwaters and wastewaters. But many of those studies on freshwaters were typically urban freshwater environments downstream of wastewater plants. And this study noted that at that time, when this was carried out, 2021, there were still few studies on microplastics in the atmosphere. I like to coin an era, I think it was about 2015 to about 2020, 2021. I call it the microplastic rush era. And a bit like the gold rush, there was this rush in microplastics research to be the first to detect microplastics, like that study that first recognized or measured microplastics in the atmosphere. There came a series of studies that were the first to find microplastics in drinking water, find microplastics in bottled water, find microplastics in the Arctic, find microplastics in the Antarctic, find microplastics in the peaks of mountains, find microplastics in Mount Everest, in the Mariana Trench, in the oceans, in human feces, in human blood, and in placenta. And I think by about 2020, it was obvious that microplastics are ubiquitous. And when we started microplastic research, some of it was prompted actually by that study by DRIS that looked at microplastics in the atmosphere in an urban setting. And when we thought, oh, I wonder if there's microplastics in the atmosphere in more remote settings. And we looked at background sites in terms of deposition, coastal sites around the island of Ireland. And we also looked at lakes, remote lakes, essentially lakes, headwater lakes that weren't close to urban centers. And we wondered at that time, would we find microplastics? I think every study now around the world knows that they'll find microplastics, that microplastics will be there. And again, as I've noted, microplastics are ubiquitous, microplastics are everywhere, and because they're everywhere, that is a quality control, quality assurance issue. Many of the initial studies didn't focus strongly, I would say, or weren't as strong in terms of their quality control. And perhaps if you're working in an environment where you're have high abundance of microplastics, that's not as much of an issue. I'll come back to talk in a few more slides about quality control, but it's a key measure, and I think as we move into the future, we need to be stricter in terms of the quality control procedures that we're applying. Another note that I have is that perhaps, this is a suggestion, perhaps the current observations of microplastics are just the tip of the iceberg. And I haven't done much work in toxicity, and at least some of the studies suggest that the current concentration is there. Toxicity, there's uncertainty about toxicity, but I'll leave that again to future lectures in this seminar series to cover. But given that we know that there's been this exponential growth in microplastics, and that microplastics in the environment take some time, or plastics in the environment take some time to break down, if we assume that perhaps what we're seeing nowadays has an age of somewhere between 20 and 50 years old, and that's taken into account that, of course, microplastics that we see in the environment are a diverse mixture from multiple sources of multiple different polymer types. And so some of them age quicker, maybe the textiles age quicker versus the larger plastic fragments that break down. But if we assume that perhaps 50 years is a reasonable average estimate for how long it's taken for the plastics we see in the environment that we're currently observing, if we look back to this growth, that's a small fraction of, or small proportion of the current production of plastics. So we're currently producing more than 400 million tons. We assume that what we see now, perhaps the breakdown of plastics that were manufactured and released or lost to the environment back in the 1970s, maybe potentially into the future, we'll see an exponential growth of microplastics in the environment. We can wait and see. But what I'll also note is that there has been some studies, I'll point to one by Finnegan et al., that looked at microplastics in the atmosphere, and they noted that in terms of the atmosphere, that studies to date had found a greater number of cellulosic fibers compared to plastic fibers. And that they believe that that very much reflected that the accumulated production of textiles up to the publication was far and away dominated by natural cellulosic fibers, and that just about now, or about 2025, we'll actually see that switch where the accumulated production of plastic fibers will overtake cellulosic fibers. And they postulated that given this overtake in the accumulated production, and of course the perhaps greater durability of plastic garments, that by about 2030 we should see a switch in the atmosphere where we're seeing more microplastic fibers or plastic fibers compared to cellulosic fibers. I should go back to some of the basics, and I've mentioned this already. What is a microplastics? And of course we know, or at least it's roughly defined as plastic particle less than 5 millimeters, so it's between 5 millimeters down to 1 micrometer, and that 5 millimeters is essentially the width of an eraser at the top of a pencil. So anything less than that is typically classified as a microplastic. And I have a link here and a note about units. Essentially, when we work with contaminants in the environment or pollutants in the environment, we typically report on a mass per volume or mass per mass units. So we might say something like micrograms of lead in a liter of water, or micrograms of lead in a gram of soil. And as I've noticed already, the most common units reported for microplastics, the number of plastic particles. Essentially, people count and they report that count. And that, again, this may be something that's initially translated from working with macroplastics in the marine environment, where counting and enumerating the number of fragments of plastic was one of the main units or measures reported. That number of plastics can also be reported as a number concentration. So it might be the number of microplastics in a liter of water, the number of microplastics in a gram of soil. And again, that number can also be presented as a number flux. So perhaps the number of microplastics per meter squared per day in rainfall. These are all very limited measures. And they're limited because, of course, if we look at the diversity of plastics out there, we're basically saying that by just enumerating them that they're all equivalent. And of course, they're not equivalent. Even if we were to say, for example, look at an example where we take a bead, a small bead, and if we measure a bead in one sample that's perhaps 45 microns in diameter versus a bead in another sample that's 4.5 millimeters in diameter, are both classed as one microplastic. So in theory, both samples, if it was two water samples, both water samples would have the same number of microplastics or the same number concentration of microplastics, 1 microplastic per liter. But of course, if they were the same polymer type, say they were PET, based just on their size alone, it would be 1,000 times more plastic in one of those samples than in the other sample. So number is a very crude measure, and it misses a lot of information. I think moving forward in the future, a combination of number and mass would be more useful. Of course, if we know the shape, the size, and the polymer type, we can easily then estimate volume and density and then work out mass. So even with some simple measures, we can translate from number into a mass value as well. And number is still important. I know there's many studies out there, and I've reviewed a number of papers where I've made some comments, and authors have come back and they've pointed out that knowing the number of microplastics is still useful, perhaps from a toxicological viewpoint, just knowing that number of particles in the surface area they cover, potential for contaminants that they might be carrying as well. So if we go back to this size range, the other thing to note, of course, is less than the 1 micron, that's a 1 nanometer to 1,000 nanometers is the nanoplastics range. And at least perhaps from a toxicological viewpoint, that's where we need to focus in the next 5 years. And perhaps maybe not just the nanoplastics, but up to about 2.5 microns in size. In terms of human health, in terms of, at least from an atmospheric viewpoint, that's inhalable plastics or inhalable size range that can go deep into the lungs. And so that's something into the future to focus on. Ignoring that for the moment, I know that we're not there in terms of measuring plastics. There are a few things we know in terms of just the count of plastics. So we know that the count of plastics, as you get smaller, the number of particles increase. And that's just a general trend that I've scribbled on there. But if I can, it's more than likely that this follows some type of exponential growth in terms of the number of plastics. And in the literature, there are many studies that, of course, report number of microplastics and also measure the size of microplastics, measure the largest length, so the axis with the largest length, and they report those, and they'll often maybe report something that looks a little bit like this. And again, this more than likely just reflects the technique in terms of how they count. You can see that drop off as they get smaller, which more than likely reflects our inability to count at smaller and smaller ranges. And I think it's been stated, and at least from our own experience as well, once you get down to about 50 microns, it becomes more difficult to detect microplastics, at least using visible techniques, so microscopy work, or on a bright field microscope. And I would say we have confidence down to about 50 microns. We do measure things lower than 50 microns, but it's true that we do see that drop off, which really doesn't reflect the drop off of the environment. It really just reflects that drop off in our ability to measure and count microplastics less than 50 microns. The other thing I'll note, of course, is that as you get smaller and smaller, the mass of those particles decrease as well. And I think I'll note this just more so for a bit of comfort from my own work, in that, of course, the fraction greater than 50 microns represents the larger mass of plastic. So even if we can't count down to the lower one, we're still capturing perhaps the larger mass of plastics in the environment. And that still is important because they're the feedstock that will go towards breaking down into smaller and smaller microplastics and nanoplastics. So it gives us at least some indication of the burden in the environment, and at least that pressure in terms of larger microplastics breaking down into smaller and smaller nanoplastics. Another key component in terms of microplastics is that definition in terms of whether they're primary or secondary microplastics. Primary microplastics refer to microplastics which are manufactured to be small. So, of course, that's the microbeads, whether they're within medicines or cosmetic scrubs. And then secondary microplastics are those larger pieces of plastic which break down, age, and weather and fragment over time. And we typically then classify microplastics based on their shape. We have fibers here in the top left, and they're essentially breakdown of textiles, clothes that we wear, as we wear them, as we wash them, etc. So wastewater treatment plants receive large amounts of these fibers through washing machines. But again, many studies have shown that wearing clothes made of plastic fibers, that they will shed and break and be released into the environment. There's pellets or nurdles. These are essentially the feed source, the feedstock for microplastic production. And again, these pellets are often less than 5 millimeters in size, and there have been many escapes of those into the environment. Films that can be enumerated as films, and again, they can be large but very thin, and these are typically breakdown from plastic bags and packaging. We have fragments, which is, I think, the most diverse array in terms of breakdown of larger plastic pieces into smaller plastic pieces, irregular shaped. We have foams, which point to typically one or two smaller polymer composition of plastics, so typically low density polyethylene. And as I've noted already, we have microbeads. And as we observe microplastic environments, as I said, we count them, we typically measure their size as well, and we note the type of microplastics. And this is, I guess, a first indicator or potential indicator of the source, knowing whether it's a film or a fiber, a pellet, microbead, fragment, foam, etc. Give us some indication of the source where those microplastics come from. And of course, that shape is important to know. If you know the size and you know the shape, you can work at the volume. And if you know the polymer type, that allows you to know the density, combine all that information, and you can actually estimate the mass of plastics as well. One thing I don't have on the list here, of course, is tire wear particles. Tire wear particles are increasingly gaining more attention. Number of studies that have looked at modeling of atmospheric transport have noted that tire wear particles seem to be a particle that can be distributed widely. And there's growing interest just in terms of the chemicals that may be really leached from tire wear particles. I'll also note, just from an atmospheric transport point of view, that fibers have also been identified as particles that potentially can travel much further than may be suggested, given some estimates of their potential deposition velocity based on size, etc. And again, I have one note. I want to come back here and again refocus on that idea of the size of microplastics and where fibers fit into that. The definition of microplastics states less than 5 millimeters. And so if we have a fiber that's 5.1 millimeters, it's technically not a microplastic. But if we have, say, for example, a plastic bead that's 4 millimeters, it is a microplastic. But of course, the mass of plastic within the two of them, assuming that perhaps, again, they're both PET, It's about 20,000 more times plastic in that 4mm bead than there is in this 5.1 millimeter plastic fiber, with assuming an average width of about 20 microns. So again, perhaps it's worth rethinking exactly what that definition of less than 5 millimeters means, and if we should rethink it. To some extent, at least to me, it seems a little bit absurd that a fiber that's 5.1 millimeters isn't a microplastic, yet a plastic bead of 4 millimeters is a microplastic. Typical workflows. I think the next guest lecture or seminar, and the next lecture in the seminar series will talk and discuss analytical techniques. So I won't mention them too much here. I'll just kind of highlight the overall workflow, and I'll cover some of the workflow that we use. And I think I'm always very surprised when I talk to people about microplastics analysis. I assume everybody does it the same way, and it's common sense, and it should be just a standard way. But even with the same media, I'm surprised at how many variations can creep in, and the differences, procedures that people can use, even small differences, just as different solutions for density separation. These are minor, but between sieving and drying and separating, I'm really surprised about the range of techniques that are out there. I've broken the workflow down into 3 stages. There's typically some field sampling component. Once you have that environmental media, then there's that microplastic extraction phase. That's where you're separating your plastics from your environmental media. And then there's that identification stage. And ideally you separate so they're as clean as possible. I note a few things that, of course, within the environment, you want to make sure that you've collected representative samples. You want to make sure that, depending on your media, you reflect the diversity of microplastics. And of course, depending on the environment you're working in, you want to make sure that your sample volume, your sample size means that your microplastics that you're collecting are above your limits of detection. And again, with blanks, that's a key thing about having blanks. With blanks, you can work out your level of detection, and you need to ensure that at least, ideally, you're an order of magnitude higher that in terms of what you're measuring in the environment. I'll note a little bit just here about this diversity of plastics, some experience that we've had. We've worked in, and representative samples, we've worked in remote environments, say, for example, some Arctic environments, or even in some of lakes that are more remote, background lakes, and distant from large urban centers. And initially with our sampling, we were collecting a few liters of sample, and based on a couple of reasons. One is we knew there were background, we knew that the dominant pathway to those environments was atmospheric, and felt that through the atmosphere there would be this natural filtering, so we would have a lower diversity of plastics, and that we could capture that diversity in smaller volumes. But we need to make sure that our volume that we're capturing was at least large enough to be representative and ensure that we're above our limits of detection. And so we've moved in these more background environments to ensure that we capture at least a 5-liter sample of water, so that we know that we're in a microplastic count range that's well above our limit of detection. In the same way, when working in more urban environments, we know we have a much richer diversity of plastics with many more different polymers, many more different sources, and a greater range of perhaps what are called shape types between foams, beads, films, fragments, fibers, etc. Perhaps in these more background environments, they may be dominated by fibers. I'll hesitate a little bit there, but dominated by fibers. And so we've moved to collect larger volumes of sample, and just so that we can be sure that we're collecting that diversity of sample. And again, some of the earlier work, I think, in the aquatic environments used large volume net captures to ensure that we captured that diversity of plastics. Of course, the limitations with nets is that there's a net and the mesh size, and of course you can lose many of your microplastics, so there needs to be that balance between capturing the diversity and ensuring that, of course, you have a representative sample, that you're not missing a certain fraction. In terms of the microplastics extraction, that's the time when you focus on separating your microplastics from your environmental media. The things to note there, that if your units are count, that you need to make sure that your procedures are gentle enough so that you're not actually breaking and fragmenting plastics in the process, that if you break your fibers to whatever extraction process, whether it's some sonication or some stirring method, that you're not actually creating microplastics or fragmenting them in the process, so that you're increasing your count. And of course, if there's any heating involved, you need to make sure that you're not melting. And lastly, in terms of the identification, that's of course when we're counting them, we're measuring the size, we're looking at the shape, and we're detecting the polymer type. And techniques are developing. I'm sure we'll hear about some of the newer analytical techniques. There's some analytical techniques now that can actually just measure the mass straight away. So GCMS with a pyro inlet will allow you to measure your mass of plastics, but you still miss out count, size, shape. And so many users of those find that they're using a kind of two parallel process where they're measuring, I would say, is the more traditional way with count, shape, size, but also then quantifying the mass of microplastics using a pyro approach. As I've noted already, given that there can be differences either in the identification, extraction, of the field approaches, studies are rarely compatible owing to these differences in the methods. And I kind of feel to some extent that the more we know about plastics, the greater the increase in research studies that are published. Feels that we still don't know much. We haven't moved very far. And that's partly because we can't expand our knowledge based on this accumulated knowledge across studies. I can give some examples and say that we've measured lakes in Ontario, microplastics in remote lakes in Ontario, and compared them to more urban lakes, and expected, of course, that the more urban lakes from other studies would have more microplastics, but they've reported lower counts in the literature just because they've used different filtering or size exclusion techniques, and perhaps lost many of the plastics that we would have counted in our study. So we ended up finding more microplastics per liter count number than they've reported in their more urban studies, primarily because of difference in that size in the field sampling process. So that makes it difficult to compare. There have been a few studies. I know Dr. Veronica Nava will talk about the Galactic study in a few weeks' time, where they applied a consistent methodology across all study sites, and all analysis was focused at one institution. And that is a really valuable study design because it allows us to build up knowledge and know that the difference between sites isn't because of methodological issues, but rather an actual difference in the environment. And once we have that diverse array of sites, we can start to ask questions of what drives microplastics. Why do we see hotspots? What are the potential drivers? By some simple modeling just based on land use around those sites. I'll note another thing, of course, again, many studies report differences. There's many studies, for example, in the atmospheric world, there are many studies that say, oh, the atmosphere is dominated by fibers, and there's many other studies that equally say, oh, the atmosphere is dominated by fragments. That could be regional differences, but I more or less suspect that the studies that count microplastics using a visual inspection are limited to greater than 50 microns. And therefore, I think in that fraction greater than 50 microns, we are dominated by fibers. But as we start to move lower than 50 microns, fibers start to break down, their length and their width become less distinguishable. And so lower than 50 microns, more or less all fibers start to become fragments. And if you can count lower than 50 microns down to 1 micron, I think you'll see a dominance of fragments. But of course, the issue here is we've got these different ranges that are maybe being counted, and it makes it difficult to compare between studies, whether that's count, whether that's dominance of a shape type, and of course, dominance of a certain size. And so again, those difficulties make it just hard to compare and accumulate knowledge. Again, studies perhaps need to qualify. Here's what the count is based on a greater than 50 micron observation count. And again, sometimes depending on how you identify your microplastics at the last stage, that whatever that technique is, whether you're using FTIR or Raman for a single particle, whether you're using a focal plane array and you have got some scanning ability, or you're using some GCMS with a pyro inlet, your microplastic extraction and your field procedures may change depending on how you measure at the end. So I think depending on that polymer composition, how you estimate that polymer composition, that can have an influence on your extraction and your field sampling procedures. For us, I show a figure here that gives an example of soil, but it's general more or less across all the field sampling we do. Going from field to filter to file, essentially that microplastic data collection. We've got some field sampling where we try to capture a representative sample in the field. Again, depending on the media, there may be some subsampling or some mixing procedure there that we do to process that sample, so sample processing. For soil, of course, we try to take soils across a wide range and then composite, so we have better reflection, say, for example, of a field, given that soils don't mix so well. But in an aquatic environment, we may be collecting a large volume of water, and we may sieve that to a fraction that will just be filtered, and then a coarser fraction that may go into the next stage, which is the microplastic extraction. So essentially into either a digestion or density separation stage. We then try to capture those on a filter paper. And from there, we typically enumerate those microplastics using a microscope, and we carry out some image analysis. And once we've captured those microplastics, we'll typically go and do some polymer identification using a Raman or FTIR on a particle by particle basis. And then, of course, collect our data for analysis. And I'll just step into one or two of these a little bit more. Essentially, I'll focus a little bit more here now on the microplastic extraction and the image analysis stages. In terms of the microplastic extraction, these aren't needed for all media, but in general, there's typically a digestion phase where you're trying to remove organic matter content from your sample. So if it's a soil, we'll digest. We typically use a Fenton's reagent. So this is hydrogen peroxide plus iron 2. Iron, that helps at least to speed up the reaction or make the reaction a little bit more vigorous. Heat can be generated. So it's important to make sure we have a nice bath on hand. Again, if it's an aquatic sample and we have high volumes of organic matter, we'll go through that process as well. Sorry, this is timed. I forgot to take the timing off. We may then, of course, do some sieving so that we can move on to a density separation. Again, if it's a particle like sediments or soil, we'll have a density separation where we try to float out our plastics. And we typically cover a number of density separations. We'll do a water density separation followed up by 1 or 2 sodium iodide density separations. Other people have used zinc chloride, sodium bromide, and sodium chloride as well. These solutions more or less do the same thing, they just differ in density. Last step, we filter that supernatant. And we've captured our plastics on a filter paper. We then move into some visual detection stage. It's tedious. Ideally, that extraction phase has resulted in a filter paper that's as clean as possible with microplastics easily identifiable. Some people do dye the plastics so that they're easier to see. Some people also use something like Nile red so that they fluoresce. We found that many of the things fluoresce as well, so it can be a challenge. So typically we inspect, we use some criteria to identify the microplastics, and then we typically follow up with a hot needle just to confirm that it's a microplastic. In through that process as well, of course, we're or photographing them. There's image analysis, which I'll just cover in the next slide. But typically, once we've identified the microplastics, we move them to another slide where we can analyze them on a particle by particle basis, so we can capture the spectra for that polymer. And I'll just quickly note about visual analysis. If we spot a microplastic, we typically take a photograph of it. We'll measure its length and its width, so we have at least 2 dimensions in terms of its size. We know the shape as well. In addition to the bright field microscopy, we'll also use a blue light to help us see some plastics that might fluoresce, and these may be clear plastics that are more difficult to see under bright light. And as part of that image analysis process, we'll often use some type of image analysis software, of course, just to measure the basic X and Y axis. But something like ImageJ can also carry a particle characteristics analysis, so we'll come up with measures such as area, roundness, etc. We've looked at these. We're not so sure how useful they are, but they may be at least useful in terms of perhaps modeling amounts of masses of plastic. We may come up with better predictors of roundness, may also better predictors of mass there, but also roundness may indicate some type of aging as well. And last on this, we use a Bruker Loomis 2. We mount them in a slide, so that works well for particles that are greater than 50 microns, less than 50 microns. We can use a transmission mode on a filter, but these aluminum oxide filters are quite expensive, and they are a bottleneck in that process as well. And once we capture that spectra, of course, there's many libraries. I like the online open access library, OpenSpeccy, and typically you compare your spectra that you've captured for your plastic against some library and use a polymer matching, essentially a Pearson R-square, to identify the probable polymer. I think this is my last slide in this, and I won't cover other work. This is just a note about quality control. It's a key step. Field blanks are really important. We try to come up with field blanks that are the exact same media. So often we'll bake soils to remove plastics and then use soils in the field as a blank. Again, we may filter water and then bring water into the field if we're doing water sampling. A key component is negative control blanks. So within the laboratory, we always have a laboratory or process blanks. They allow us, of course, to understand contamination. So we can assess throughout that process the potential levels of contamination that we've picked up through the whole processing stage in the lab. But again, if we've collected blanks in the field, they'll go through that whole process. And again, with enough blanks, it allows us to assess the limits of detection. So are we measuring plastics in the environment that are above a limit of detection based on our blanks? Positive controls are becoming more and more important. So spiking our samples, spiking our blanks, so that first of all, we can assess recovery. But I think a key move now into the future is, of course, spiking it with a range of plastics that are more consistent with the plastics we're seeing in the environment. So large colored beads, they're easy to recover, but they may not reflect what we're seeing in the environment. So a range of sizes and a range of shapes, I think, are important in our spikes. And of course, a range of sizes as well, going down to smaller ones, so that they can actually, if we're counting in a visual sense, they allow us to quantify how good we are at getting to lower and lower sizes as well. So if we believe we can get to 50 microns or less than 50 microns, of course, we want some type of spike that is in that same size range to confirm that we can actually detect plastics within that size range. For us, of course, all solutions are filtered, so we filter everything, even our water. Everything is rinsed, triple rinsed with RO water after cleaning, and that's filtered RO water. Everything is covered when not being actively used. And of course, we wear lab coats that are cotton. We try to wear cotton clothes, etc. We try to use fume hoods, negative pressure environments. And often we put out air blanks, so something that's on the bench while we're working, but we also recognize there's maybe little value in those that, of course, process blanks and spikes are much more valuable in terms of our analytical procedures. So I'll end on this list. Common challenges. Units are really crude and perhaps limited value in reflecting the amount of plastics that we're seeing in the environment. Science is rapidly changing, and I think we're moving towards perhaps easier detection, quantification in the environment. Unfortunately, most of the equipment nowadays promises more than they actually deliver. I feel many of the equipment manufacturers are like car salesmen or car person salesmen, or car person, anyway, salespersons. They promise a lot, and still, I think many people come up with those same bottlenecks. They're difficult. They're difficult to process large number of samples at a high speed. Again, given that we've moved from the marine environment and there's a lot of interdisciplinary work, some of the science can be a bit fishy. I've seen many studies that have reported atmospheric measurements, but the siting criteria for their measuring sites don't meet what I would say is standard siting criteria for a monitoring station. So they were in closed areas that didn't have open airflow, etc. I think a key limitation of this reporting is the fact that everything is lumped into less than 5 millimeter. And of course, it seems a little bit absurd that a fiber that's 5.1 millimeters isn't a microplastics, yet a bead that's 4 millimeters is a microplastic, given that the mass of plastic between two of them is by far and above in favor of the larger bead, or the bead at least. Given the difference in methods, comparison is difficult. Given that plastics are ubiquitous, quality control is extremely important. It's difficult to separate microplastics from the environment. We really want to move to techniques that can extract out as clean a microplastic as possible. That facilitates at least more rapid detection of the polymer type, more rapid counting, more automated counting, but it's often very difficult to separate plastics from the environment. And current methods are tedious and time-consuming. And potentially we're at the tip of the iceberg in terms of what we're seeing in terms of microplastics. And I think I'll stop it there, given that I'm already over time.
Thank you, Julian. So maybe the people can give some questions.
While people are thinking about questions, maybe I will ask you one, Julian. And it comes to one of your early slides where you showed that the microplastics we're seeing now, you think are back from the 1970s. Given that exponential graph that you showed, how much of that post-1970 plastic do you think is recoverable before it becomes microplastics, or is already at the point where it's irretrievable?
Yeah, well, hopefully one of your lectures in the series will be able to answer that. Yeah, again, what we see now, I think, is that diverse mixture, and some of them are newer plastics, perhaps 5-10 years old, but I'm fairly certain some of them are much older plastics, 50 years old. So I think there is this potential that we will see this exponential increase in terms of microplastic counts, number concentrations, observations in the environment. I think that we do have some scope to capture. The question is, capture and move to some disposal. We did some work with biosolids. We looked at biosolids, and of course, as you know, biosolids are in wastewater treatment. Up to 99% of plastics in the waste stream end up in the biosolids. And in Ontario, at least, those biosolids then, a large proportion of them are spread onto the land, which essentially means that they're being, exported onto the land, and then they potentially can wash off. And so we looked at some zero energy measures, just settling and stirring to see if we could promote microplastics into the upper layer of biosolids, and then by scraping off the smallest amount of the biosolid as possible, could we come up with enriched concentrations of microplastics in the biosolid? And I think the simple answer is yes, we can. And so we can recover perhaps more microplastics from the biosolid waste than just delivering them to the land, but it's still a small fraction. So I think some of those techniques, again, the challenges of microplastics, the diversity of them, their ubiquity, mean that it's, again, maybe they're very leaky systems and it's tough to capture a large amount of them. So yes-ish, but I look forward to a future lecture on this.
Okay, thank you. So may I ask a question? So I think it's you gave a very good introduction for the microplastic research in the environment. So because the size, when you talk about the, like when you're doing the, so for example, the sample in soil, right? You take some samples. So talk about if the size is smaller than 15 micrometer, it will be very difficult. So what will be the limit like for the detection, in terms of the size?
Yeah, well, I think what I've reflected there is a workflow that we use, which is, primarily visual inspection. We know that, of course, we have to move to something that's a little bit more, so we don't have to manipulate the plastics. And so essentially, if we use transmission mode in FTIR or focal plane array, if we can get our filters clean enough, we can use a scanning approach that will allow us to detect microplastics down to 3 or 4 microns in size. And of course, with Raman, you can get down to about 1 micron. So there are techniques out there. At least my general experience is these are still difficult procedures. They're still tedious. They're slow in terms of analyzing large numbers of samples. Even single samples, it's a long time to process one filter paper. So I think we have those challenges in terms of that throughput and the speed of the work. But of course, there are new techniques out there, and again, in the atmosphere, I've seen a number of studies that have used, say, as a combination of pyro techniques and automated counting techniques to assess microplastics in the atmosphere, so they have a smaller count size range. But there's still few studies. There are very few studies that, for example, that have assessed microplastics in the atmosphere in the PM 2.5 fraction of the atmosphere. There's only a very few studies that have done that. I think at the moment a handful. So I think the techniques are starting to emerge. The challenges are the different environmental media, and at least what I can say to some comfort, that even if we're limited by those techniques, being able to count greater than 50 microns still means we're capturing the kind of mass or the burden of microplastics in those different media. So we have some sense of sites that have a greater pressure, greater mass of plastic that will break down to smaller and smaller nanoplastics.
Thank you. So I think that some people just type in the message board.
Yeah, I see that. There's one that says, what do you think, what is or are the most challenging for microplastic research? And I think the two challenges is, one, it's rapidly changing. So we have this, it's very difficult to compare to previous studies. And of course, just the processing of samples currently at the moment, that workflow is slow and tedious. And I think that's a bottleneck in terms of understanding distribution, the abundance, the type of microplastics in the environment. I think many people also claim that access to equipment to identify polymers is also a bottleneck as well. There's many people in universities that are sharing a machine amongst multiple users, and so that's also a bottleneck. There's another question, what should be the focus in the future? I think it is this focus towards smaller and smaller plastics. If from a toxicological viewpoint, they're the plastics which we are more easily inhalable, ingestible, etc. So being able to quantify those, I think, is an important step into the future. And I know from an atmospheric viewpoint, we collect PM in the atmosphere on every 5 minutes. It's reported on an hourly basis. We have decades of measurements that we can look back over time. We need to get microplastics at that same resolution so that we can actually assess whether there's some impact of those microplastics on human health from an atmospheric viewpoint. And again, that can be the same from other disciplines as well, whether it's an aquatic in the food environment, etc. There's another one says, do I know about sampling campaigns to detect micro and nanoplastics in atmospheric samples? There's a link there. I know of a few studies that are soon to be published that have looked at nano microplastics, and again used multiple techniques to quantify smaller size ranges, but also used pyro techniques to quantify the mass of microplastics, and at a time resolution that allows them to bring in trajectory analysis so they can actually more efficiently assess sources as well. And again, as I've mentioned, this bottleneck is the challenge is time and processing those samples. As techniques develop, we are seeing a few studies now that can capture atmospheric microplastics, at least the ones I'm familiar with, at a shorter time resolution, every 2 hours over a short period of time, but combine that with trajectory analysis so that it can help understand potential sources of those microplastics. Someone's asked about whether we can see adverse effects of microplastics on different organisms. And I'm happy to say somebody else is going to cover that topic. I'm not as familiar. I think for the moment, really where we work on is trying to quantify them in the environment and a focus on more background remote environments, looking at the atmosphere as the main transport pathway. I think the only thing, at least in my opinion at the moment, the toxicity issue is uncertain. But if we do see an exponential increase in microplastics in the environment, well, maybe we'll all end up being smothered by microplastics. I think I've covered all the questions.
Yeah. Okay, thank you. Thank you very much. Doc?
What I could show two last slides quickly. We've been using, and it's just to mention for a project. So I'll just scroll through a load of slides to ignore. Luckily, we ran out of time. This is a project a pilot project that we're currently working on. We've under the Air Convention, the UNECE Air Convention, every 5 years there's these large-scale MOS surveys that are carried out, and those MOS surveys are carried out primarily to look at atmospheric deposition of trace elements. So MOS is widely used as a biomonitor of trace metal deposition, and they carry them out every 5 years and assess the recovery or the response of the atmosphere to reductions in emissions. In collaboration with this group, we've looked at MOS and we said, okay, MOS have a high surface area and they actually seem to retain microplastics that are deposited from the environment. So we've set up a pilot project. The project is known as Microplastic Acid Deposition Assessment using MOS in Europe. So it's the MADAM project. And there's 3 or 4 institutions. Essentially ICP vegetation is run out of the UK Centre for Ecology and Hydrology. That's the International Collaborative Programme on Vegetation, looking at the impacts of air pollution on vegetation. There's the IUTA in Germany, and then we're working with the University of Siena. And we have a trial MOS survey in place. Essentially, we ask the members of ICP vegetation to volunteer to go out and collect sample using a common protocol. So more or less, we stole the study design from Galactic. We had put together a common protocol. Volunteers went out and collect samples. We had about 35 countries that went out and collected samples, and they gave 1 to 3 samples per country. And then these samples were essentially separated out. So we have a replication across 3 institutions. So between Trent and Siena, we have a batch of all the sites, UK Centre for Ecology and Hydrology, and then UTA in Germany. And we're carrying out the same analysis, but using different techniques. And we're hoping that it'll be a way for us to look at microplastics across this broad area, evaluate mass as a biomonitor, methods comparison, and also perhaps a tool for source identification. Once we have these consistent capture data sets, we know that perhaps the difference that we're seeing between sites isn't based on our methods, but an actual reflection in the environment. I should note that, of course, biomonitors are great, but they don't reflect true deposition. They reflect some accumulation on a tissue, in a tissue surface. So we're not trying to estimate deposition from this. I think what we're trying to do is just look at how the signature of microplastics may change across these sites in Europe. So the dominance of different plastic types, or the dominance of different shapes, or the mass of plastics. And it's the last slide if it works. This just shows the capture sites that we have in the study. And the dots here don't indicate anything in terms of measurement, but just the population distribution within a 5-kilometer radius of all of our study sites. So we can see we've got this gradient in terms of different anthropogenic pressures on these sites. There's a couple more sites on this since we've sampled here, and there's actually even some sites in, yeah, I can't remember, further east, and there's more further north as well. So, Doug, if we move forward on this, I might present some of this in Chile, if I'm invited.
Okay. You are obviously more than welcome to present this in Chile. We would look forward to hearing about that. I just want to, I know we had 2 or 3 people who joined later on in the talk, and I want to remind people that the lecture will be posted on our YouTube channel and on our website, so you can review the talk if you want. And Julian did mention some of the upcoming talks. We will be having a couple of analytical talks, a talk on aging. We will get into some toxicity, and hopefully towards the end, we'll even start to talk about whether there are some solutions to this obviously very serious problem. So I want to just thank you, Julian, and hope that everybody will join us next week.
See you next week, Doug.
All right. Bye-bye. So next week will be the same time. So we'll see you next week. All right. Thank you, Julian. Thank you.
Thank you very much. Bye.
Bye. Bye, Doc.